This lecture will mark the start of our discussion of plane elasticity. We're going to take the general three-dimensional elasticity problem and reduce it down to 2 dimensions. A lot of problems that are practical in nature can be reduced to 2 dimensions, and they're a little bit easier to solve using various techniques that we'll study and learn about in this section. We're going to take a look at 2 different types of plane problems. One is in plane strain, the other is in plane stress. We'll start with plane strain. In these problems, instead of having a fully 3-dimensional state of strain, the non-zero strains will lie in one plane. So if we think of our stress element and have a similar thought about having a strain element as well, we could have strains that are in the plane of the material in the x and y directions, and a shearing strain gamma xy, or 2 times the tensorial shearing strain epsilon xy. We can have these strain components and the other ones are 0. Now we don't have to call the plane in which the strains are non-zero the xy plane. We could have it as the x and z or the y and z instead. But the idea is we can identify one plane where primarily those strains are non-zero. Even in this particular plane, we could have 0 strains in, say, the y direction or a 0 shearing strain. But in general terms, these will be our non-zero different strain components. We can have a great reduction in the governing equations from 3D elasticity down to 2-dimensional elasticity in this case. The trace of the strain tensor, epsilon II, or little e, in terms of displacement then, would be the partial of u with respect to x plus the partial of v with respect to y. Our third strain component would be 0, so the partial of w with respect to z would be equal to 0. So I'll just note that these are displacement components. We have our general stress-strain relations. We can cast these in terms of the Lemay coefficients. Sigma ij is equal to lambda epsilon kk, or little e, times Kronecker delta ij plus 2g epsilon ij. Well, when we can reduce this problem, we can write this as for example, sigma x being equal to lambda e plus 2g epsilon x, sigma y being equal to lambda e plus 2g epsilon y, sigma z would be equal to lambda e, well, plus 0, since epsilon z is equal to 0. Let's go ahead and write these down. Epsilon z is equal to 0, gamma x z and gamma y z would all be equal to 0. We can have our shearing stress, tau xy, would be equal to g times gamma xy, the engineering shearing strain, or in terms of displacement would be equal to g times the partial of v with respect to x, the displacement in the y direction, plus the partial of u with respect to y, displacement in the x direction with respect to y. And of course, our shearing stresses tau xz and tau yz would both be equal to 0 since the respective shearing strains are equal to 0. We can take a look at equilibrium. In general, we have sigma ij comma j plus the body force per volume b sub I is equal to 0 for our equilibrium equations. But since some of our stresses are equal to 0, we can reduce this down. We have the partial derivative of sigma x with respect to x plus the partial derivative of tau xy with respect to y plus the body force in the x direction, I'll call that capital X at this point, equal to 0 for equilibrium. We have partial derivative of tau xy with respect to x plus the partial derivative of sigma y with respect to y plus the body force in the y direction is equal to 0. And lastly, for our third equilibrium equation, we would have capital Z is equal to 0, the body force in the z direction. If we notice, the partial derivative of sigma z with respect to z is equal to 0, since we have no, since that's a constant. Sigma z is a constant according to our equations above. So for our state of plane strain, when we reduce our equations of elasticity, we do need to have an enforcement that the body force in the z direction is equal to 0. Let's go ahead and write down the strain displacement on this page as well. We've already mentioned that the strain in the x direction is a partial of u with respect to x. Strain in the y is a partial of v with respect to y. And then epsilon z is equal to 0. And that gamma xy is equal to partial of u with respect to y plus partial of v with respect to x. And that gamma xz and gamma yz are both equal to 0. Alright, this is going to be kind of an important page. You may want to write these down. We're going to do some manipulations on these things. The first of which is we're going to add the normal stresses sigma x and sigma y. Let me make a little bit of room and we'll do that. Alright, so we'll add these two terms together. So sigma x plus sigma y will be equal to lambda e plus 2g epsilon x plus lambda e plus 2g epsilon y. We can add these lambda e's together. And we can write it this way if we would like. Let's go ahead and split these back out. We have a g epsilon x and a g epsilon y. Now recall for the plane stress problem, plane strain problem, that epsilon z is equal to 0. And so little e then will be equal to epsilon x plus epsilon y. So this term that I'll highlight here is the same as little e in the case of plane strain. So we can rewrite our sigma x plus sigma y as being equal to 2 times lambda e plus g e, trace of the strain tensor. And we can pull that out as 2 little e lambda plus g. We did some manipulations with the other elastic constants, E and nu. Poisson's ratio is lambda divided by 2 lambda plus g. So if we want, we can also express sigma x plus sigma y as being equal to lambda over nu times little e. Now if we wanted sigma z, which is a constant, sigma z is lambda times little e, and so we can also express this then as Poisson's ratio nu times sigma x plus sigma y. We can move that Poisson's ratio over to the other side. And so sigma z is not an independent value when we have a situation of plane strain. So sigma z is dependent on sigma x and sigma y. We're going to use that to our advantage. When we have plane strain, we only have 3 independent stresses. The 4th stress, sigma z, is a dependent quantity. And furthermore, we can write our strains in maybe the more usual form. Epsilon x is equal to 1 plus nu over e. Sigma x minus nu, sigma x plus sigma y. Epsilon y is equal to 1 plus nu over e. Sigma y minus nu, sigma x plus sigma y. And the engineering shearing strain gamma xy is equal to 2 times 1 plus nu over e tau xy. And the last bit of information we need to know is our last governing equation is the compatibility equation. And in this case, we just need to worry about one of these. The second partial of epsilon x with respect to y twice, plus the second partial of epsilon y with respect to x twice, is equal to the second partial of gamma xy with respect to x and y. Alright, well, let's keep these equations in mind, and next we're going to take a look at generalized plane stress. So we talked about plane strain or generalized plane strain, and now we'll talk about generalized plane stress. And in the end, we're going to see that the equations that we get, the governing equations, the functional form of these equations is very similar, not completely the same, but very similar to the ones that we have just written down here. Alright, so with generalized plane stress, it is kind of analogous to generalized plane strain. In this case, though, our non-zero stress components lie in one plane. And I'll put a little asterisk by that. Typically, this plane is the x and y plane where we have our non-zero stress components, but we might have a constant stress sigma z. Plane stress is a fairly common state of stress, or at least an approximation to a fairly common state of stress that exists in thin sheet. In thin sheets where the stresses are primarily applied in the plane of the material, it's very difficult to get a meaningful stress gradient through the thickness, and oftentimes that stress through the thickness is very small, approximately 0, or constant. In contrast, plane strain is often common in very thick components where the deformation is constrained in the z direction, is what we would typically call. So to illustrate this thin plate type of geometry, I'm going to try to draw kind of a thin plate. And I'm going to use the dimension of the plate in this direction. I'm going to call that h to stick with what our textbook is showing. In the plane of the plate, we'll call that the x and y directions. And perpendicular to the surface of the plate, we'll call that the z direction. Okay. So we have surfaces on the top and bottom of the plate, and these surfaces are traction free. Okay, so there's no stresses on the top and bottom surface, although like I mentioned, we could have a constant sigma z, and we'll get to that in a moment. The other stresses we're going to assume are symmetrically distributed about the middle surface of the plate. So if I were to zoom in on this portion maybe of the plate, there would be my thickness h. I will draw the middle surface of the plate in here as a dashed line. And we'll just note that the other stresses are distributed symmetrically about the middle surface of that plate. So that little circled region is kind of that region blown up. Now, due to this symmetry about the middle surface of the plate, or this assumed symmetry that we're going to have, the plate quantities can be expressed in terms of middle surface quantities. So the mid-surface can represent a reference for all of our deformations and all of our stresses and all the things that go on in that plate. And so we can use mean values for these different kind of quantities. So for example, the displacement in the x direction at the middle surface, I'll call the mean value of the displacement u. It's going to be a function of the coordinates x and y, but not a z. we can use the average value type function in calculus. We can take an integral from plus or minus h over 2 of the more general displacement field. That can be a function of x, y, and z. We can integrate that and divide that by the thickness, and then we would have our mean value for x displacement. Likewise, the mean value of the v displacement as a function of x and y would be expressed in a similar way based on the three-dimensional displacement field, little v of x, y, and z. This reduction down to 2 dimensions is often seen in finite elements. For two-dimensional finite elements, continuum-type plate elements, you'll use and define a middle surface value and a thickness, and then bending stresses and so forth are extrapolated out to the top and bottom surface away from that defined middle surface. We can also have displacements in the z direction, and we can indicate that by a mean value as well. And these would be, again, based on similar expressions for the full displacement field. It's a function of x, y, and z in the z direction, that little w integrated over the thickness and divided by the value of the thickness. We can also get mean strains in our material in a similar type of way. If our strain displacement then for the mean strains would use the mean displacements. Our top and bottom surface would be traction free, although we said we could have sigma z, but we'd still have tau xz and tau yz equal to 0 on plus or minus h over 2. And our equilibrium equation then would look something like partial of sigma x with respect to x plus the partial of tau xy with respect to y plus the partial of sigma 3,3 plus the partial of tau xz with respect to z plus the body force in the x direction per volume equal to 0. We can have a similar body force term for the second line. Let's go ahead and write that out. Partial of tau xy with respect to x plus the partial of sigma y with respect to y plus the partial of tau yz with respect to z plus a body force in the y direction is equal to 0. Of course, with these two going away, being 0, we can get rid of those terms there. And our third equilibrium equation is worth a little bit careful look as well. We would have the partial derivative of tau xz with respect to x plus partial derivative of tau yz with respect to y plus the partial derivative of sigma z with respect to z plus a body force term in the z direction equal to 0. Now these two terms being 0, what we're left with is partial derivative of sigma z with respect to z. If sigma z is constant, then the partial derivative of sigma z with respect to z is equal to 0, and we're left with the condition that the body force in the z direction is equal to 0. So very similar to our case of plane strain, in our case of generalized plane stress, we're going to have a situation where we're going to make the reduction down that we're going to neglect the body force in the z direction. All right, we can talk about mean stresses. We can talk about stresses that are defined on the middle surface of our thin plate. We can define those in the same way. We'll put the little bar over it. Eventually we're going to drop the notation with the bar, and it'll be kind of understood that we're talking about middle surface stresses. So we have our stress on the middle surface sigma x 1 over h, integrated from minus h over 2 to plus h over 2 of sigma x integrated over the thickness in the z direction. And likewise, similar expressions for sigma y bar and tau xy bar.